Now I will come here. Example 6.5, that is a two-way slab design. Design the marked 4 panels of monolithic RC slab shown in figure 6.14. The building is to be used for the residential purposes, and US customary bar sizes are to be selected. Use concrete grade 18 megapascal and grade of steel, that is 280 megapascal. So now I will go shown in figure 6.14. So that is the picture. Okay, so that is the picture. There are 4 slab panels, 1 2 3 4. In this example we have to solve this all 4 slab panels depending upon the boundary conditions. Either it is a one-way slab panel or two-way slab panel. So here the clear lengths and the spots, all first condition is meeting, that all slabs are supported by edges. So this is also wall, this is either wall or beam, okay. All slabs are supported by edges. So this edge is discontinuous, this edge is also discontinuous, and slab panel of 1, this edge is continuous. Similarly, this edge is continuous. So all slabs are 4 panels. Similarly, slab 2 have only this edge discontinuous, this edge continuous, this edge continuous, this edge continuous. That is the second case. Third slab has one edge continuous, discontinuous, continuous, and the slab 4 have all edges are continuous. This is continuous. So our all 4 slabs are supported by edges, either by beam or wall. So here slab panel 1 2 3 4. Slab panel 1, it's shorter span length, longer span length. Okay, here slab panel 1, its clear length in the shorter direction, that is 4500, in the longer direction, that is 7000 millimeter. The spots are 2 to 8 millimeter. It means all the spots are walls. Okay, M. Now we calculate the M for the calculation of slab thickness. M is longer to shorter span. So longer to shorter span, that is answer is 0.64, approximately equal to 0.65 for two-way slab. In the definition of two-way slab, we have the idea that longer to shorter span should be less than 2. Then we call that is a slab of two-way slab. So here we divide longer to shorter 7 divided by 4.5. Our answer is 1.5, that is less than 2. It means that is a two-way slab. So but here you are saying that is a shorter to longer span. So here 4.5, that is a shorter divided by longer span. So answer is 0.64. Okay, so what is that? Why we are doing the shorter to longer? That is a just mathematical equations, but we can get the same idea, like if your slab panel ratio is in between 0.5 to 1, so that is a two-way slab when we divide shorter to longer. Like you can check that if 1 divided by, or you can say 6 meter divided by 6 meter, you are getting 1. So that is a two-way slab. So and second, if you are having 5 meter divided by 10 meter, okay, or you can 10 by 5, that is a 2. So that is a two-way slab. So here when we divide 5 by 10, you will get 0.5. So it means 0.5 to 1. If you get the values between 0.5 to 1, so that is your two-way slab. Okay, so that is a smaller difference. that from the theory because all the coefficients, why we did that, and all the coefficients and the minimum slab thickness formula are given in the terms of shorter to longer span. So that's why we are doing M. So here M, that is 0.65. Now for slab panel 2, its one dimension is 6000 millimeter and the other dimension 7000 millimeter, means shorter is 6 meter, longer is 7 meter. M is coming 0.86 and we are rounding it to nearest that is available in the table, that is 0.85. Again two-way slab, the third panel 3.5 divided by 6, 3.5 divided by 6, this dimension 3.5 divided by 6, answer is 0.58 approximated to 0.6. Why we are approximating it here? In the ACI coefficient we have the values intervals of 0.05, so 0.5, 0.55, 0.6, so that's why we are rounding to nearest available value of M. So here in the third condition we got the M value 0.58 to nearest value available, that is 0.6 approximated to. So panel 4, one dimension is shorter span 6 meter, longer span 7 meter. So M value is Lx over Ly. So answer will be 0.98 something. So that's why it is approximated to 1. So now we got the idea that all 4 slabs are two-way slabs, and we also got the M values. Now if we have the M value, now we can calculate the minimum thickness for each slab panel. So here before going to slab panel, first of all we will identify the cases, that which case we will follow. In the one slab panel you can understand that your two edges are discontinuous, means there is no slab panels are present on the other side. So that is discontinuous edge, this is discontinuous, and this is continuous, this is continuous. Here you will select the case where two edges are discontinuous, two edges are continuous. Okay, in this second, one edge is discontinuous, three edges are continuous. Okay, you will get that case, that is where three edges are continuous, one edge is discontinuous. In the 3, one edge is again discontinuous, 3 edges continuous. Okay, so we will pick that case. And the fourth, when all the edges are continuous. Okay, here shorter side is in this case slab panel 2, shorter side, that is 6 meter, 7 meter is discontinuous. Okay, in the case 8, longer in the slab panel 3, longer dimension is discontinuous. So what is case 4, case 9, case 8, case 2? So here I will go back in the ACI coefficient method. Here we have to pick the coefficients corresponding to cases. So what our case? So here okay, so currently we assume that we do not know what is case 4, case 9, case 8, case 2. We only know that our in the slab 1, our one longer and shorter is discontinuous and longer and shorter is continuous. Similarly in slab panel 2, one shorter is discontinuous, all 3 is continuous. And in the slab panel 3, one longer is discontinuous, all 3 are continuous. And in slab panel 4, all edges are continuous. So let's see our slab panel 1. when two edges are continuous, two edges are discontinuous, we will move in this table. 1, no, 2, no, 3, no, 4. You can see here. The slab panel 4, one longer and shorter are discontinuous, one shorter and longer are continuous. So our case is 4. So now we will move further. For 3 edges are continuous and 1 edge is discontinuous. So when we'll move, okay, here one longer edge is discontinuous, here is one shorter edge is discontinuous. So our case is 9. So for slab panel 3, one longer edge is discontinuous. So here you can see case 8. Okay, so all the edges are continuous. Okay, you can clearly see that is our case 2. Okay, so we will go corresponding to that table and corresponding to that table column coefficients, we will pick that coefficients for the designing of moments. Okay, so now for each slab panel we have calculated the M value, shorter to longer. So H minimum, shorter span ratio for slab panel 1. So our slab panel 1 shorter span clear span length is 4500 into 0.8 plus 280 grade of steel divided by 1400 divided by 36 M. M is 0.64 plus 9. So our H minimum for panel 1, that is 140 millimeter, that is greater than 90 millimeter. Okay, second slab panel, H minimum in the second slab panel, our shorter span length is 36 meter. 6000 plus 0 into 0.8 plus 280 divided by 36 into 0.86. I will go back. What is the M value for panel 2? That is 0.86. That is just we rounded up for the looking of coefficients, but the actual values are here 0.86 plus 9. 9 is in the formula that is given by the code. H minimum is 150 millimeter. Then similarly for slab panel 3rd 0.58, for slab panel 4 that is value 1, and you have to put the shorter span length. So for each slab panels we got the minimum thickness 140 millimeter, 150, 117 millimeter, 133 millimeter. So for all slab panels, if we provide 150 millimeter slab, because the difference is not too much for the each slab panel, so if we provide the 150 millimeter slab panel for this panel 1, 2, 3, 4, so you can understand the 150 millimeter slab thickness will satisfy all slab panels. So in this example, for equal depth, H 150 millimeter is provided. Now for in this two-way slab, we have to design the moments in the two directions, in the shorter and the longer. So D for short direction, that is D for short direction, that is 150 minus 27. In the 27, what is 20 millimeter is the clear cover, and 7 millimeter is the number 13 millimeter half dia bar. So 20 plus half of 13 approximated to 7 millimeter, so that is a 27 millimeter. D for short direction you got 150 minus 27 equal to 123 millimeter. So D for long direction that will be 150 millimeter minus 38 millimeter. So in that 38 millimeter, what is that? So 20 millimeter is the clear cover. Then you got 13 millimeter for the main bar, and for the distribution bar, or you can say in the long direction, that is for half of 10 millimeter bar. So that will be 5 millimeter. For 10 millimeter bar you will plus 13 millimeter plus 5, that will be 18. So you have to subtract 20 millimeter. What is that? For example, these are the main bars. This is the distribution bar. So from center of the main bar, you are getting the D value 123 millimeter. To get the value from the center of that is the slab bottom. So to get the value from the center of the distribution or the long direction bar to the bottom, so 20 millimeter is the clear cover, then 13 millimeter main dia bar, and half of 10 millimeter bar, so that is 5 millimeter. So that is why you have to minus 38 millimeter to get the effective value for D. D is the from top fiber of concrete to the center of steel. So our for D for long direction, that is 112 millimeter. Now we have decided the D effective depth depth of our slab sections, then D effective depth for short and long direction. Now we will move for the loadings. Here we have selected 150 millimeter slab. So for the weight of 150 millimeter slab, that is 150 divided by 1000, to convert into meter, multiply by 2400. Concrete density, that is the concrete density, reinforced concrete density, so that is 360 kg per meter square. 75 millimeter screed of brick ballast means 75 millimeter brick ballast on the slab, that is 75 divided by 1000, multiply by density of brick ballast means density of brick, so that is 135 kg per meter square. So PCC, plain cement concrete plus tarazu, that is chips, so 60 millimeter divided by 1000 density of PCC, and tarazu approximated to 2300. So our value of PCC plus tarazu, that is 138 kg per meter square. So our total dead load, that is 633 kg per meter square. And for this example, for residential buildings, the live load value, that is 200 kg per meter square. You have to pick the live load value depending upon your building type. If that is a residential, you will pick the value from the table that is given in the chapter 1 of this book, or you can pick the live load value from ASCE 7, American Society of Civil Engineers 7. Okay, so for this residential building, the live load value 200 kg per meter square is picked. So now for the factoring, we have to multiply the dead load with 1.2, and for the live load, that is to 1.6. Why we are separating multiply with 1.2, 1.6? Because in the previous pages of this book, I have shown you that the coefficients are given in terms of positive dead moment, positive live moment, and negative moment for the three conditions. So that's why I have we have separated 1.2 dead, that is 7.45 kilonewton per meter for unit strip, and 1.6 QL, 1.6 into live load, that is 3.14 kilonewton per meter. So here we have calculated the total 1.2 dead plus 1.6. The total moment is total load is 10.59 kilonewton per meter. So we have calculated the load on the slab. The minimum steel here, that is 280 grade steel, 0.002 BH, that is B is for unit strip, that is 1000 millimeter, and H is 150 millimeter. So our answer is 300 millimeter square.